Hi, this is Jinang Kim. Currently, I'm working at Samsung Electronics and my role is developing some tools for developers. In this presentation, I introduced the paper named Automatic Abnormal Log Detection by Analyzing Log History for Providing Debugging Insight. This is the contents of my presentation. First of all, let me explain why we did this research. As you all know, software is not only getting larger in size, but also increasing in complexity. According to a survey of software sites, if all of Google's services are combined, it is said to be over 2 billion lines. Next, below figures show examples of software complexity. In the case of Kaizen platform developed mainly by Samsung, it is composed of various core components and they are connected to each other, so it is often very difficult to analyze the root cause of defects. The second figure shows an abstract architecture of SmartThings providing IoT device control service. Using SmartThings, you can control various devices through mobile. Since the detailed communication logic between devices is very complicated, it is also not easy to find which step generates abnormal situation. In this case, it is most impossible to reproduce the defects. As a result, analyzing collected log is the only way to get a clue to solve the defect. However, the problem is that the more complex system, the more logs are left. And even most logs contain information that is not significantly related to the defect. To solve this problem, there are various log analysis approaches. One of the most famous approaches is to define certain key indicator in advance, extract it in real time, and monitor whether there are some problems. This approach has strengths in finding exceptional events, but it is not suitable for analyzing various test scenarios. Alternatively, there are some analysis approaches based on past test history. The right figure is the workflow of the paper published at ICSC in 2017, and it computes keyword similarity to recommend the most similar defects that occurred in the past. These approaches are good for covering various test scenarios, but need improvement for precisely extracting important log lines. In our paper, we would like to introduce a new log analysis approach combining other advantages of the two approaches described above. We are calling our tool historian in the sense that we use test log history to analyze it. The figure shows the workflow of the historian, but I skipped to explain details. From now on, I will briefly explain how historian computes statistics. Basically, we use the idea of TF-IDF, which is a popular algorithm in data mining. Simply explaining, TF computes statistical value of how important a particular word in a particular document by counting occurrences. And IDF computes statistical value for how few occurrences of a specific word in a group of documents. On this idea, we consider each logline as a word, set of log lines generated during a test scenario execution as a document, and group of anti-log files as a document group. And then we compute importance and we score based on statistics. As TF is trivial, I skip this and explain some details of document frequency. This figure shows simple example of document frequency. Let's assume that we have 6 log files and we want to get important information for this one based on document frequency. It has 2 green lines and 2 red lines. Let's see the green line. It may not be important for this one as it also appears in other theses. Conversely, since the red line appeared only in this one, it is highly likely containing important information for this one. It is the concept of document frequency. Basically, document frequency does not consider time information, so we propose a new document frequency concept by adding temporal perspective. That is, whether a particular log lines appears mainly on a specific date or not. If the existing concept of document frequency for test scenarios is called DFS, then the new DF concept for time is called DFT, and we compute overall noise probability based on 2DF scores. Using these concepts, historians find abnormal log lines for given target log. More specifically, let P be the important probability of line error and Pn be the noise probability of error for given TC as at T. We find anomalously presented and missing log lines by using these formulas. First, as high score of 1 minus P means L is not usually occurred in S, and high 1 minus Pn means L is not noise. Therefore, L can be said to be an abnormal log line containing important information that it has not appeared in the past. On the other hand, high P means L is frequently occurred before in S, and high 1 minus Pn means L is not noise. Nevertheless, it is not occurred at this time. This indicates that L is an anomalously missing log line. This slide shows an example page of historian. We provide actual test log lines by highlighting anomalously appearing lines and anomalously missing lines. Now I explain some experimental results of our paper. We plan to the experiments by using Kaizen platform, which is tested through a test tool called TCT. Among various test suites, we select 3 TCTs as the experimental subject. Note that the third one is actively being developed compared with others and has a lot of network-related APIs. We first want to know how many lines are highlighted by historian. To check this, we defined a metric named debugging effort based on anomaly scores. Low D score means that developers only need to check small number of log lines for getting debugging insight. This figure shows the result for each TCT. As you can see, the average D score is about 0.04 for all 3 TCTs. This means that developers need to check only 4% of log lines when test fails by using our tool. Next, we want to check whether our tool highlights abnormal log lines well. If our statistical approach works correctly, normal log information of each test scenario is accumulated after some test passes well. Then, when a test fails, information about abnormal log lines that did not exist appears. This lists the increasement of the E-score if those abnormal log lines are highlighted correctly. This figure shows the D-score change flow during the test period for selected test cases which have at least one failure. And the first graph shows the normal flow we expected. For example, for the first thesis, they failed at day 6 and the D-score will increase a little at that date. Unfortunately, the last graph shows the limitation of current hour statistical algorithm. In this case, TC was failed at the first day and even has more fails than passes. As a result, our tool considers fail log as normal logs, so wrongly analyzed the logs. It's time to finish my presentation. In our paper, we introduce a new log analysis approach called historian. We use test history for finding abnormal log lines occurred at failed tests. And our experimental result shows that developers only need to check 4% of log lines for getting debugging insight. For the next step, we plan to support various log types, removing false alarm, improving statistical algorithms, and so on. Thanks for listening to my presentation. If you have any question, please send an email. Thanks again.